Section 5.2, Double Integrals over General Regions. Your homework is problems 60, 61, 62, 63. This might seem like a lot, but it's kind of one question broken up into several parts. So it's like one question, 68, 69, 70, 71, same thing. It's kind of the same question rolled into one, and then 91. To begin, let's talk about general regions of integration. In this section, we consider double integrals of functions defined over a general bounded region, D, on a plane. Most of the previous results hold on this situation as well, but some techniques need to be extended to cover more general case. An example of a general bounded region D on a plane is shown. That's your picture here. Since D is bounded on the plane, there must exist a rectangular region R on the same plane that encloses the region D. That is, a rectangular region R exists such that D is a subset. And that's all we're saying. That notation is just that D is a subset of R. It's contained within R. Okay, now this is kind of the punchline of this section, defining type 1 and type 2 enclosed regions. Now, if I recall when I was in your shoes and took my type variable, I think it was mostly of a setup within your argument for your x or your y, but type 1 and type 2 is how this book talks about it, and I really like this type 2 and type 1 breakdown. So your definition is a region D in the xy plane of type 1 is of type 1 if it lies between two vertical lines and the graphs of two continuous functions g1 of x and g2 of x. That is, D is equal to x comma y such that A is less than or equal to x less than or equal to b, and g1x is less than or equal to y less than or equal to g2x. Type 2, in the region D in the xy plane is type 2 if it lies between two horizontal lines and the graphs of two continuous functions h1y and h2y. D is equal to x comma y such that x is less than or equal to y less than or equal to d, and h1y is less than or equal to x less than or equal to h2y. So what we're saying in a picture is that we're trying to set up arguments either in a sense vertically in terms of x or horizontally in terms of y. So let's take a look at this first picture. This is a picture of a type 1 region. So it lies between two vertical lines and graphs of two functions of x. So we're going to look at our x values for our x. Now, as we integrate, we have to consider our functions. So I want to consider my first function that I come across, and then my second function as it comes across. And I want to make sure that this is an argument of x. Now, for type 2, we're going to consider our y-axis and then move forward, and then look at our function from our y perspective in terms of y and in terms of y to see what we enclose. Let's do an example. Consider the region in the first quadrant between the functions y equals square root of x and y equals cube root of x. Describe the region first as a type 1 and then as a type 2. All right, so let me help you walk through these type of problems. So we have type 1 and we have type 2. For type 1, my best advice is to look at the x-axis and then read your function down and up. Okay, so we're going to write our values, our enclosed values, in terms of x and in terms of y. So first, looking at x values, we see that it goes from 0 all the way to 1. So from 0 to 1. Now let's read our function. So our first graph is this one. Y equals x cubed. Is in terms of x. So our lowest one is x cubed. And then we look at the one that follows, square root of x, y equals square root of x, and it's in terms of x, so then we write square root of x. And that is our type 1. If it's helpful, you can label this point here as 1, comma 1, since we're using that endpoint a lot. Okay, let's move on to type 2. I'm going to erase my notes so that I can redraw them for type 2. All right, now for type 2, we want to read our function from the y-axis. So we want to look at the y-axis and then read our function from left to right. Okay, same deal. We want to enclose it between x and enclose it between y. All right, so let's take a look at my graph from a y perspective. So it goes from 0 all the way to 1. So my y is from 0 to 1. Now, your x is your functions that you're going to come across. I first come across this function here, but it needs to be in terms of y. So let's solve for x. So we just square both sides and left with y squared is equal to x. So that's my first one, so that I have y squared. And now my second one would be this function here. Now same deal, I need to make sure it's in terms of y, so I need to solve for x. I take the cube root of both sides so that I have x is equal to the cube root of y. And there we have it. Now, if you want to properly write your answer, remember to use set builder, and that's how your notes and how your definition has it. So just to recall set builder notation, it would be curly brackets, x comma y, such that, and then your answer. So if I want to do my type 1, for example, I would write 0 is less than or equal to x less than or equal to 1, comma, x cubed is less than or equal to y less than or equal to cube root of x. So that's how you should properly write your answers. But I like to just think of what I'm enclosing and then move from there. And you can always go back to writing your answer mathematically properly. Theorem 5.3, double integrals over rectangular regions. That's supposed to be together. Theorem 5.3, double integrals over non-rectangular regions. Suppose g of xy is the extension of the rectangle R on the function f of xy. Define on the regions C and R as shown in picture 5.12, which is that very first picture we saw in the function. In our notes, I'm sorry. Then g of xy is integratable, and we find the double integral of f of x comma y over d by double integral of f of xy dA. Okay, so next we have 5.4, Fubini's theorem. It might also be called strong form. So what this is telling us is how we can integrate using our type 1 and type 2 arguments that we did in example 1. So what we're saying here is how we're defining our integration, both for type 1 and type 2. So based on our theorem, a function of f of x comma y is continuous on region D of type 1. We have integration of f of x y dA is equal to the integral of d of f of x comma y dy dx. So what it's saying here is if we're doing type 1, we first want to integrate our argument in terms of y and then of x. Similarly for type 2, we first want to integrate with x and then with y. So let's take a look at this example here. Evaluate the integral of 3x squared plus y squared, where x comma y such that negative 2 is less than or equal to y less than or equal to 3, and x is less than or equal to y squared minus 3 is less than or equal to x less than or equal to y plus 3. So we want to go ahead and write our answer in terms of whatever bound we're given. Okay, so we're going to integrate this here, and we're left to find our bounds based on this. Now, if you like to, without doing much more work, we can already integrate because we have our function in some terms, right? If this is too confusing, you can always take a moment to write it separately. So we have x from -2 to 3, and my y is from y squared minus 3 to y plus 3. Maybe writing them all together horizontally might not let your eyes focus on it. So what we're seeing here is that our graph or our argument is set up for type 1. We have our argument in terms of our x-axis, and we're reading our functions from the x-axis. So it's set up as type 1. And you can go ahead and consider working from type 1 since that's how your argument is set up for your function. So that we have oh, I'm sorry, I wrote this backwards. I'm like, what if this doesn't make sense? Let's write this again. So for y, we have all right, so if we have it set up for y, so it's type 2. Disregard everything I talked about for the last minute. All right, so I go from -2 to 3, and from x we have y squared minus 3 and y plus 3. So this is actually type 2 because we're reading it from our y-axis, from our points along our y-axis. So if you like to, you can try to rewrite it in terms of type 1 region as you see in the picture, or you can go ahead and continue as it's given. So let's go ahead and integrate in terms of type 2. So we have the integral. Now if you'd like to, you can go ahead and label your values for your bounds. So if it's type 2, then x comes first. So we have x is equal to y plus 3, and x is equal to y squared minus 3. And for y, we have y is equal to 3 and y is equal to -2. Remember, your higher bound goes on top, your lower bound goes on the bottom. And we're integrating for the function 3x squared plus y squared. And we first are working with our x and then with our y, since we're working with the type 2 argument. Now, I'll skip through a lot of the work of integration for the sake of making the video not too lengthy. All right, so let's first integrate in terms of our x. So this means that, well, let me write this down. We're integrating for x. So recall that y isn't a constant. So if we integrate for x, our first term gives us x cubed plus xy squared. Now we can go ahead and evaluate for y plus 3 for x, and x is y squared minus 3. So I'll help you set it up. So we're going to first plug in y plus 3 for x, so that I have y plus 3 cubed plus y plus 3 minus y squared minus 3 cubed plus y squared minus 3 y squared. And then we go ahead and we FOIL. We actually have to expand all this by FOILing it out and multiplying it in. You should get at the end, after you expand, we still have y equals 3 and y equals negative 2. And we are evaluating for negative y to the 6th power plus 8y to the 4th power plus 2y cubed minus 12y squared plus 27y plus 54 dy. All right, let's integrate so that we have negative y to the 7th power over 7 plus 8 over 5 y to the 5th power plus 1 half y to the 4th power minus 4y cubed plus 27 squared y squared divided by 2y squared, 54y, and we're working with bounds of 3. Y is equal to 3 and y is equal to 2. Now remember, we integrated for y, so our x was a constant, but we don't have any more x's, so that worked out. So once we evaluate for 3 and 2, negative 2, we should end up with 2,375 over 2. There in 5.5, decomposing in smaller regions. Suppose D can be expressed as D is equal to D1 union D2, where D1 and D2 do not overlap except their boundaries. Then what it's saying is you can split up your integration based on different boundaries, different cutting points, I guess you can say. So here, let's see this example. It's pretty overwhelming to try to integrate all of this in one shot, but luckily we can break it down. Now, from looking at it, it seems like I can break it down this way and break it down this way so that we have different pictures. Let's take a look at this first part. We'll name that subset D1. Now, what would be the best way to integrate, or I'm sorry, to write your boundaries for D1? So we have to come up with one that we would like to work with. Well, if you're looking at this, do you want to look at it from up and down or from left to right? And for this first one, both of them work pretty well. When I first saw this, I don't know why the type 1 made more sense to me. So I want to look at this from my x coordinates point of view. So looking only at your x's, we see that it goes from negative 2 to 0. In my lines, it's enclosed by this line here, which is a horizontal line y equals 0. And then it's enclosed by this graph here, which we have an equation for. Y equals x squared, x plus 2 squared. And it works out to write it in terms of x because your function is in terms of x. Otherwise, you would have to rewrite it in terms of y. So let's go ahead. Type 1 seems to be the first, the ideal. So because it's type 1, we're going to go our x's from negative 2 to 0. And my function is from the line y equals 0 to our function x plus 2 squared. Now let's say I wanted to start off with type 2. We could have, but then once we got to our function, we would have realized, hey, it's too much work to rewrite this function in terms of x. Let's just go for how it's written. Okay, let's take a look at our other function, this one here. So what kind of type would be ideal? Now regardless, we still have to write it or an argument for x and an argument for y. So which one would be the best option? Well, I see our function is an argument of y, so maybe type 2 would be best. So we look at our y's, it goes from 0 to 4. Our y's go to 0 for 4. And if I look at my functions enclosed by this line here, this is the line x equals 0. So our first x is 0, and then our graph. Now, if I'm writing in type 2, which is for y, I need to have my argument in terms of y. And I do. My function is in terms of y. So I have y minus 1 over 16 y cubed. Okay, let's take a look at this third region. So again, we want to determine what type we want, type 1 or type 2. And for both, we need to enclose our x values and our y values. Okay, taking a look at this, I think y kind of works better. Also, I see I'm going to have to enclose it within this line and this function. This line is the vertical line, x is equal to negative 2. But what is this other line? Well, it comes from this function here. So it's x is equal to y minus 1 over 16 times y cubed. So it seems because it's in terms of y, type 2 would be best. All right, so for my y functions, it's going to be from negative 4 to 0. And my functions I have is this function here that I have in terms of y. So it's negative, well, we read from left to right. So this one would be first. We have negative 2, and then y minus 1 over 16 y cubed. And if you look, I already made a mistake. You always write our lowest and our largest. Our lowest would be negative 4. Negative 4 to 0. Okay, so these are our regions. We have different types of procedures. Okay, now we can go ahead and try to integrate. We're going to write it as a sum. So let me write this first one. Let me pick a more darker color than that green. Let's take this first region, this D1, and write an integral for that portion. So we have type 1. For type 1, we were looking at the x. So type 1 means let y be first in integration. So that we have, now we're enclosing it and we're evaluating for this integral here. So we have 2x plus 5y, and we're going to start off with y. I have y is equal to x plus 2 squared, and y is equal to 0. Our x's go from 0 to negative 2, so x is equal to 0, x is equal to negative 2. We said y is first, so dy dx. Next, I'll do in blue. We have this other region. We should have called that one D2. We're going to write a plus, and we're going to set up our integration. Because we have type 2, meaning we worked with the y's as our region we're enclosing, we want to start off with x. So start with x when integrating. So we have x is equal to y minus 1 over 16y cubed to x equals 0. And for my y's, I have 4 and 0. The function we're integrating is 2x plus 5y dx dy, because x is first. And then lastly, this third region, I'm all out of space. I'll continue down here. This is type 2, so we want to integrate for x first. Okay, our x boundaries are from y minus 1 over 16y cubed to negative 2. Our y boundaries are from 0 to negative 4. And our argument for which we're integrating for is 2x plus 5y. Whew. All right, so much work to break it down. But now we still have even more work to do. We have to integrate for these three portions. Now, I trust you can integrate, so I'll leave you to finish this off. Your answer should be 1,304 divided by 105. Changing the order of integration. As we have already seen when we evaluate an integrated integral, sometimes one order of integration leads to computation that's significantly simpler than the other order of integration. Sometimes the order of integration does not matter, but it is important to learn to recognize when a change of order will simplify our work. It's supposed to be a W. All right, so in this example, it's asking us to reverse the order of integration for the integrated integral, then evaluate the new integrated integral. So our integral is from the integral from x equals square root of 2 to 0, and then y is equal to 2 minus x squared to 0 of e times e to the x squared dy dx. So we see here, we are integrating for y first. So this tells us that this is type 2, meaning we're looking at our function from left to right. We're looking at our y argument. So we want to change it. We want type 1, meaning we want to look at our x argument. I said that backwards. If y is first, I was right about that. If y is first, then it's type 1, meaning we have our argument in terms of x. So our hopes is to change it to type 2, meaning we look at it from our argument from left to right. All right, so I include this picture so we can flow through it a bit more quicker. So I see that we want to work for type 2 from our y standpoint. So looking at our y's, it goes from 2 to 0. Let's set up our bounds that we're going to write. Our y goes from 0 to 2. Now, what are these arguments? So I have this line here that's enclosing this x equals 0. So my x goes from 0, and then you have an argument in terms of x. Now my argument's in terms of y. So I need to rewrite it so that I have y is equal to, I take the square root of both sides, get x squared. Let me show that work. 2 minus y, and we go ahead and we can move the 2 over. So I have x squared minus 2 is equal to negative y, 2. And then we divide by negative 1, so we're left with 2 minus x squared. So I have 2 minus x squared as my argument for y. Oh no, that one's right. Maybe I should write my notes. So we want to look at y. Want to look at y argument. So this is in terms of y. So we have our x. We have this line at x equals 0, and then x is equal to the square root of 2 minus y. There we go. All right, now we have set up for type 2. So we want to integrate this double integral. Because it's type 2, we want x first. So we have dx dy, x is equal to, and then y is equal to. For x, we go from the square root of 2 minus y to 0, and for y, we go from 2 to 0. And we're integrating for x times e to the x squared. All right, let's first integrate for x so that we have 1/2 e to the x squared. And then we evaluate when x is equal to the square root of 2 minus y and x is equal to 0. And we are left with 1/2 times e to the 2 minus y minus 1. Now we evaluate in terms of y. Y is equal to 2, y is equal to 0, dy. So we integrate, and we're left with negative 1/2 e to the 2 minus y plus y. From 2 to 0, and our answer is 1/2 e squared minus 3. Now I did skip a lot of integration steps because I don't want to make the video too long. Another example. Consider the integrated integral from f of xy dx dy where z is equal to f of x comma y of x equal to x minus 2y over the triangular region R that has the sides x equals 0, y equals 0, and the line x plus y equals 1. Sketch the region and then evaluate the integrated integral, first with respect to y and then with respect to x. Okay, so we want type 2 and then type 1. Okay, so let's go ahead and start off with type 2. So type 2, we want to read it from left to right. So we look at our function from left to right, and we see that our highest and our lowest point is 1 and 0. And that is for y. So we have 0 through 1. Now I want to look at my functions that I come across. The first function is this one right here, this vertical line x equals 0. And then I have this next line here. Now I want to make sure that it's in terms of y. So I have x equals and then y some argument. So I use this one here, x equals 1 minus y. So I write 1 minus y. All right, now let's go ahead and write that type 2 argument. Well, we did type 2, let's do type 1 in terms first with respect to x. For type 1, you erase those notes. We want to look at our graph from the x-axis on up. So let's enclose our x values and our y values. So from x, we start at 0 and we end at 1. So from 0 to 1. My first line that it's enclosing is y equals 0. And then I come across this line here. Now because I have it in terms of x, I want y equals in your argument of x. So 1 minus x. And there we have it. Now we can go ahead and write these two separate integrals. So for type 1, let me try to fit it in here. We would integrate. Now because we're writing in terms of y, x is first when we integrate. So we have x is equal to 1 minus y, x is equal to 0, y is equal to 1, and y is equal to 0. Now we're integrating for the function. It's telling us that it's x minus 2y. So x minus 2y dx dy. Now for type 2, type 1, we're writing our argument in terms of x, so we integrate for y first. So I have y is equal to, and then we're going to have x is equal to, and when we integrate, it's going to be dy dx. So for y, we have 1 minus x to 0, and from 1 to 0 for x. And we're integrating for the function x minus 2y. All right, I'll let you integrate yourself. You'll see you'll get the same answer in return. What should you be getting as an answer? Should be getting negative 1/6. So you can go ahead and check your work for that. Next example, find the volume of the salad bounded by the planes x equals 0, y equals 0, and 2x plus 3y plus z equals 6. All right, so I give you these pictures here. So this is the enclosed triangular figure. Now we wish to find the volume of that. Well, we can go ahead and look at a certain perspective, enclosing it from your x and your y axis, so that we have this triangle. Now we see that you have many options to work with, right? You can use type 1, you can use type 2, whichever one is of your preference. Now it's just asking you to find the volume. Okay, so to enclose our value, to get to our picture here, we're going to make z 0. So if we let z equal 0 so that we can work with that function, we have 2x plus 3y equals 6. And that gives you this line here. If you want it in y equals mx plus b form, you can go ahead and do that. But this also gives us a function for which we integrate. So we'll integrate for the function z is equal to 6 minus 2x minus 3y. So we're going to try to find our integrated integral for 6 minus 2x minus 3y. Okay, now it's a matter of you determining whether you want to do it in type 1 or type 2. Let's go ahead and do type 1. If we choose to do type 1, let me give some little notes for myself so I can avoid making a silly mistake. We're going to evaluate in terms of x. So we want to look at the x values. And then look up and down. I actually say down and up for our functions. Okay, so for our x's, I go from 0 to 3. And for my y's, I'm looking at this first graph here, which is y equals 0. And then I stump along this graph here. So I have to solve for y. So that we get y equals negative 2 over 3x plus 2. So write negative 2 over 3x plus 2. Okay, now we can go ahead and write our integration. Now because it's type 1 in terms of x, you're going to let y be first when you integrate. So I have y is equal to, x is equal to, x is equal to, dy dx. All right, let's write our bounds. For y, we have from negative 2 over 3x plus 2 to 0. And then for x, we have 3 to 0. And we're integrating over, need more space to write, 6 minus 2x minus 3y. We said y is first, and then x. Now again, I'm not going to show all the integration work, because then this video will be extremely long. So you should get 6 as an answer. I'll let you integrate that on your own. Next definition, the area of a plane bounded in region D is defined by the double integral of D, 1 dA. Let's do an example. Now here it's asking for find the area of the region bounded below by the curve y equals x squared and above by the line y equals 2x in the first quadrant. All right, so because it's asking for the area bounded, we know that we're integrating over 1. So now our job is to determine what type of argument we want our bounds to be in, type 1 or type 2. Now, if you notice, everything is written in terms of x. So type 1 would be ideal because I wouldn't have to change my functions too much. But you can also do type 2 if you like. We can set up both and then you can try whichever one you like. Let's set up both. All right, let's do type 1. Now this is in terms of x. So you look at your x values and you look at your graph or your functions down and then up. Okay, so our x's go from this point here is 2 comma 4. So we go from 0 all the way to 2. So from 0 to 2. And our first graph is this graph here that we come across. That graph is y equals x squared. So we write x squared. Our second graph we see is y equals 2x. So then we write 2x. Let's now do type 2. So for type 2, we're considering our y values, or it's in terms of y, and you want to look at your graphs from left to right. Let me erase my notes. That point's important though. That point there is 2 comma 4, where those two functions meet. So if we look at our y values, our graphs go from 4 to 0. So my y argument goes from 0 to 4. And then our x graphs, we come across this graph first. So I need x equals in terms of y. And we have it right there. We have y over 2. And then we have, in terms of y, x equals square root of y. So then we have square root of y. So if we wanted to integrate, because it's an area of a region bounded, it's not telling us what we're integrating over. We should know that we're integrating over 1. So let's set up our type 1. For type 1, since it's in x values, right is first when we integrate. So I have y equals. I'll have y equals 2x and then x squared. When x is 2 and x is 0 for 1 dy dx. Now type 2, we're integrating for y, well in terms of y, so then you let x be first when you're integrating. So we have x is equal, y is equal, y is equal. X is equal to square root of y to y over 2. And x is from 4 to 0 because it's the area we're integrating over 1, dx, dy. All right, so then you go ahead and work out this integration. It's not so bad. Your answer should be 4 over 3. We can also use double integrals to find the average value of a function over a general region. The definition is a distinct extension of the earlier formula. So we're going to do the other formula we did. We're going to do that first, and then we're going to integrate over a given function. So for this example, we're asked to find the value of the function f of x equals f of x comma y equals 7xy squared on the region bounded by the line x equals y and the curve x equals square root of y. All right, so for this next problem, we're asked for the average value of the function. So we know to proceed with our definition above. Now to do so, we first need to find the area of the region bounded, just like we did before. So let's first find the area of the region bounded. Now I see that everything's in terms of y for our function. I have x equals y and x equals square root of y. So let's proceed with type 2. All right, so for type 2, we're looking at our y's, and it goes from 0 to 1. And our arguments, our first graph is x equals y, and then x equals square root of y. So if to find the area of the enclosed region, we're going to integrate over 1. Because it's type 2, it's in terms of y, we let x be first when we integrate. So I have x equals, and then y equals secondly, dx dy. So we have x equals square root of y to y from 1 to 0. All right, we find the area of over the enclosed region for 1. And if we do that, let's do that work really quick. If we integrate for 1, we get x. We evaluate when x is equal to square root of y and x is equal to y. So that we get square root of y minus y. Now we integrate in terms of y equals 1 and y equals 0 for square root of y minus y dy. And our answer will be 2 over 3 y over 3 over 2 minus y squared over 2 from 1 to 0. And we evaluate. Our answer is 1/6. Okay, now to find the average value as our function is asking for, I first need to find my area of my region bounded, which we did. So our new part that we have by our new definition would be 1 over 6 times our integration. Now we don't have to change anything, we just have a new function for which we're integrating. So I have y equals 0, y equals 1, y equals 0, x equals square root of y, x equals y of 7x y squared. And once you integrate that, your answer will be 21 over 20. All right. Next we have a new theorem, and it works pretty much the same as we have. So 5.6 Fubini's theorem for improper integrals. If D is a bounded rectangle or a simple region in the plane defined by f of x comma y of a less than or equal to x less than or equal to b, and g of x less than or equal to y less than or equal to h of x, and also by x comma y of c is less than or equal to y less than or equal to d, of j of y less than or equal to x less than or equal to k of y, and f is non-negative function on D with finitely many discontinuities in the interior D, then we can integrate over the enclosed value. It is very important to note that we required a function to be non-negative on D for the theorem. to work. We consider only cases where the function has finitely many discontinuities inside that D. So in general, we can proceed and integrate as normal within an enclosed region. And this example is just the same as the examples we've done. So I'll let you try that one on your own. Now for this section that we've gone over, it's pretty lengthy. Now the integration that you're doing is a lot like what you saw in your previous calculus course. What's different here is what we're enclosing in and in what terms we want to work with. So that's 5.2, double integrals over general enclosed regions. Thank you.